Hey guys, this is the last section of chapter 4, finally, related rates. Related rates are the thing in calculus that are, for many people, are one of the hardest things to do, but it's actually one of the most useful things to do. I'm going to give you step by step how to do these problems. We're going to do a bunch of these problems, okay? And then we're going to do a bunch in class. We're going to spend a lot of time on this. I'm even going to turn the light on in this room because to shed some light on all of you, my peeps. Okay, Calc, let's do this thing. Let's do it. I'm gonna give you a handout with this on it, so you aren't sitting there writing feverishly. Okay. First thing you should always do, and this is ridiculous stuff, but yeah, no, do it. You must understand the problem being asked. You have to know what they're looking for and what they give you before you start to answer the question. Always know what you're looking for before you start looking for it. Okay? I know that seems silly. It's not like you're going to go, oh, I'm going to go treasure hunt and I'm just going to go walking around with a shovel and digging holes. No. You look for something specific and then you have a general idea of where it is. Okay? 2. Develop your model. Same as before. Draw pictures. I'm going to draw a picture for almost every single problem we do. Make sure we label the picture correctly and we see our parts we need to find. Okay? So picture, we change this picture into an equation. Okay? And then we make a variable for what we want to find out and make it so we can do so. Okay? These are mostly going to be geometric because we're dealing with the real world. The real world is shapes and such. And then we're going to differentiate both sides implicitly in terms of time. Because we're going to take the derivative in terms of time because time is something that we actually go through. I mean, this is going to be real stuff, not theoretical. These are things that we can find out and see what's going on. Make sure we use our chain rule. You guys are pros at implicit, so I'm not very worried about this. Next, we take everything we know and we plug it into the equation. Okay, we freeze the picture because we're looking at a given exact moment. How fast is a car going? A rocket? How much is our volume changing? How much water is coming out? What do we need to do to fix this chili? Okay, that's actually a problem we might see in class. We're going to do one like that in class. Then it's just algebra. And then 6, we take our answer and we translate it into a different language, the math language. We make sure it makes sense, their units match up. Units are going to be important on these problems. Did I make my point clear? Okay. I'm going to see how long this long intro took. Oh no, what's happening? What? Why are we watching this video?
Just a good old boy. Never meaning no harm.
Watch out, sir. Oh, no, record it now. Don't put your gun on.
Straightening the curve. Flattening the
That's right, this is school program.
Someday the mountain will do the book along never will.
Oh, Uncle
Making
Dad.
their way. They know how. That's just a little bit old.
Cooter.
Just a good old boy.
Oh,
Change if they could.
Batman boss on.
Fighting the system like a true modern
Oh,
day Robin Hood.
that's physically impossible. I'm sorry. Nope. Watch it again. Whoa, what just happened? Why did we do that? Because the Duke boys are running away from Boss Hog. You see here? We got the police cruiser, Boss Hog, is approaching a right-angled intersection from the north. It's chasing a car, the Dukes. It has turned the corner and is now moving straight east. The cruiser is 0.8 miles north and the car is 0.6 miles east. The police say the radar, the distance between them is increasing at 50 miles per hour. The cruiser's moving at 60. How fast is them good old Duke boys going? Okay. So what are we looking for? Well, we are looking for the speed of the Duke's car. Speed of car. Of Duke's car. Okay. Number 2. I'm doing the steps from before. I'm gonna draw a picture. Okay. So we have a police car, the Popo. Lights on it. Flat siren. No. Okay. They're north, right? We got them Dukes are east. Never eat soggy waffles. So we got them Duke boys. 2 of them. I can't draw General Lee, so I'm not going to try. Okay, here's your intersection. Okay. Now, them Duke boys is 0.6 miles east. These guys and about 0.8 miles north. Okay. Now, I'm going to name these. I'm going to go X, Y, and Z. Okay? So you guys can kind of see what I'm doing. I know what Z is too, right? Because I can do 0.6 squared plus 0.8 squared equals Z squared, right? When you do this, you end up getting Z is 1.0. It's a 3, 4, 5 triangle. Okay? Pythagorean theorem, right triangle. Okay? Now, I'm going to get a little bit tricky. So, our derivative of y in terms of t, that means our change in y in respect to time is going to be what? The police speed at a given moment, instantaneous velocity. Our dx over dt, if we took the derivative in terms of t, that's our change in x given a time, like miles per hour, change in distance over time. That's going to be dim good old Duke boy speed. And they were speeding. And your dz over dt is going to be the change in distance between them. Between the cars. Okay? Okay. I'm going to pause this for a second. I'll be back. I decided I'm going to try and finish this one. Now I got to put this into an equation. Now when you make your equation for related rates, you have to use all your variables from your original. So what equation relates x, y, and z? Well, we used it already. You could say x squared plus y squared equals z squared. Okay? And again, you just have to make an equation with all the variables so that way you can go back and solve it later. So 4, you take the derivative in terms of time. So for 4, you take the derivative of this in terms of time. Doing implicit differentiation, you get 2x, derivative of x, over derivative of time. You gotta do your chain rule. Because you don't know what the derivative of x is in terms of time. It doesn't just become 1. Because before, when we take derivative of y, we're doing it in terms of x. But now we're taking the derivative in terms of a different variable. You get 2y dy over dt. Then you get 2z dz over dt. Okay? Now, we go to step 5. We plug in what we know. Well, we know x is 0.6. So that's going to be 2 times 0.6 times dx over dt plus. Now what's y? Y is 0.8. You get 2 times 0.8. Now, do we know the police copper speed? Yeah, they're going 60 miles an hour. If they're going 60, it means their speed is 60. But now, this is where it gets really, really tricky. Really, 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 really tricky. Now, are they increasing that distance or decreasing that distance on that y? They're decreasing it. So their speed, I should say velocity, is actually going to be negative 60 because they're getting, that distance is getting smaller. Okay? Equals 2 times my z was 1.0. Now, what was the change in between? The distance between them and the car was increasing at 15 miles an hour. So increasing tells me this is positive 15. Okay? Now I can cheat here. So when you multiply some stuff out, you get 1.2 dx over dt, which is what you're looking to find anyway, so we're good. We want to find the Duke speed. Plus negative 96 equals 30. So we do some algebra, and we divide by, we add 96, and we get 1.2 Duke speed, derivative of x in terms of time, equals 126. Divide by 1.2, and you get the Dukes. We're going about 105 miles per hour. So 6, when we interpret it, I already did it. The Dukes were going 105 miles per hour east. Woo-wee! Okay. Alright, Calc kids, another example for you. Suppose you have a width A and length B of a rectangle, and the functions are functions of t in terms of time, and let A be the area of a rectangle. Find the equation for dA in terms of time. Okay. So we got a rectangle, right? And that's length times width. In this case, we're going to call it A and B. So our area equals little a times b, right? Right. So what we want to find is the derivative of this whole mess in terms of t. So what we get is dA over dt equals, oh no! What's the derivative of a times b? Well, what we do is we have to use our good old product rule. U is a, v is b. So the derivative of a, well, is dA over dt. And our derivative of b, which is v, is dv over dt. It's your decibels over time. It's actually not. We do our cross multiplication dealio. You get a dB over dt plus b ruh-roh reggy. Let's get these out of the way. Plus b times dA over dt. And we're done. That's it. Product rule with variables and letters and such. Okay, one more example, guys. One more. So suppose you have a ladder leaning against the wall. The bottom of the ladder is being pulled away from the wall at a rate of 8 feet per second by some jerk who's pulling you down on the ladder. At what rate is the area of the triangle changing in square feet per second at the instant the ladder is 3 feet from the wall? So first, what are we looking for? We're looking for what rate is the area of the triangle changing. So we're looking for rate of triangle area changing. Right? Number 2, we need a pitcher. Oh boy, oh boy, oh boy. Okay, so we have a wall. We have a ladder leaning against the wall. That's our ladder. And this is in grass and stuff. This is the ground. And then you have some jerk deadlifting the ladder. You know they're jerks, they have slanty eyebrows. Pulling it out from under you. And so you're like, oh no. Eek. Because they're not very nice. Okay. So again, I'm going to call this, well, let's see what I did call it. I did this before. I'm going to call this wall X, Y, and Z again, because I really like those. Now, our Z in this one, the ladder is 5 feet, right? And that's never going to change. So if we think about that, our derivative of Z in terms of time, our ladder is constant, right? So what's the derivative of that ladder going to be? How much is it going to be changing? Well, it's constant, so it's 1. Okay? So now let's take a look at Y. We're looking for when Y is 3 feet from the ground. Okay? So the big question is, well, and then dy over dt is what? 8 feet per second. Because that's how fast it's getting pulled out. And it's positive because that length is going to get longer as you pull out that ladder. Okay? So now when we look at the wall, first we need to find out how tall this wall is. Or the distance between the top of the ladder and the ground. Well, we need to use Pythagorean theorem, or we can use the fact that this is a 3, 4, 5 triangle and say that's 4 feet. Okay? Because 3 squared plus x squared equals 5 squared. Okay, 3, 4, 5 triangle. Okay. You know, 5-foot ladder, 8 feet a second. Okay, do we have everything filled out we know? What is the area? Okay, we're good. That's our picture. Now we need to make an equation. Equation's going to be x squared plus y squared equals z squared. Okay? Or another equation we're going to have to look into, but we aren't going to do yet. So hold on to your horses. Because another area we should keep in the back of our head is 1/2 base times height is area of a triangle, right? In this example, 1/2 x, y is our base and our height would equal the triangle area. So keep that in the back of your head. 3, we take the derivative. Again, since it's in respect of time, you're going to have to put 2x dx over dt, okay, plus 2y dy over dt. If you want to use primes for this too, it's fine. Equals 2z dz over dt. Okay? Just look at why we did in the last example. Okay, we're still taking our derivative in terms of time. Third. Fourth, we plug in what we know. Well, we know x is 4. But we don't know what the change in x is. Okay? We know y is 3. We know our change in y is 8 feet per second. Okay? Now, we know z is 5. And our dz is 1. Okay? So when I plug this all out, you get 8 dx over dy plus 6 times 8 is 48 equals what? I'm sorry. I told you guys something way, way wrong a long, long time ago. If this is constant, it means our change is 0. Okay? Because it's never going to change. So your slope is 0. 0 slope. No derivative. So this equals 0. My bad. I don't know why. I haven't written down my notes right. And I know that's 0. But for some reason, in my head, I want it to be there. But no, it's 0. Because the derivative of a constant, like 5 is your equation. The derivative of 5 is 0. Okay, so you get 8 dx over dy dt t equals negative 48. So your change in the height of the wall at a given moment is negative 6 feet per second. Okay? And that's going to be important because we're going to need it when we go back to this equation. Okay? Because you could say, oh, that's our answer. It's falling. You are falling downwards at 6 feet per second. Because that's how far you're falling. But no, I digress. That's not our answer. Because what were we looking for this whole time, guys? The area. Okay? So we have our dz, dy, dx. We have our x, y, and z. So now we can actually go back and solve what we needed. Step 3, take the derivative of this beast. Okay? Uh-oh, product rule. U is x, v is y, u prime is dx over dt, v prime is going to be derivative of y with respect of t. Don't forget about this 1/2. So you get 1/2 x dy over dt plus y dx over dt equals that area we're looking for. Okay? Now, we plug in our values again like we did before. 1/2. Our x is 3. Our dy over dt is 8 feet per second. Plus our y is 4. Our change in x is negative 6. And that's going to equal our change in our area. And so when we plug that into our calculator, we get well, let me see here because I don't feel like doing it. You get 1/2 times 14. So you get 7 feet squared per second. Okay? Because it's change in area, which means at the point, that's the change in area, because we're doing number 6 right now. This was 5. So we didn't have to really solve for anything. That's our dA over dt. So number 6, we interpret it as the change in area of triangle when ladder was 3 feet from base was 7 feet squared a second. Okay? Okay. That's it for today. I might make another one. We might do just 2 more in class.